Hi, welcome back. So this is looking at molecule polarity, but this is part number 2. So when we left in part number 1, we were talking about which of those shapes were symmetrical. So just another reminder, only the listed shapes are symmetrical. All the rest are non-symmetrical. And only those listed shapes, they're only symmetrical as long as the bonds are all the same. So they have to be the same type of bond. If there's any differences in terms of the bonds, then those molecules are no longer symmetrical. And we'll do an example of that. Now, the second set of rules is to determine the actual polarity of the molecule. So there are 4 rules that help us determine whether the molecule is polar. So let's write in black here instead. It'll be a little bit easier to see. So is the molecule polar? Okay. So in the first instance, if you have an ionic bond, then the molecule is automatically an ionic compound. But I want to remind you, ionic bond needs 2 things to occur. A difference in electronegativity that is greater than 1.7 and a metal. So even if the difference is greater than 1.7, if the bond is between 2 nonmetals, then it is not an ionic bond. So just keep that in mind. Okay, so if we have an actual ionic bond, then the compound itself is ionic. Okay, in the second situation, so if we have only nonpolar bonds, can't spell polar apparently, so if we have only nonpolar bonds, then we are automatically a nonpolar molecule. Okay, so if all we have are nonpolar bonds, or if our bonds are all nonpolar, we have a nonpolar molecule. Okay. In the third situation, so we only have one bond, so only one bond, and it's a polar bond, we are going to have a polar molecule automatically. Okay. You'll notice that in these first 3 situations, we don't actually even need to think about the symmetry of the molecule, and we'll actually only need the symmetry of the molecule in the 4th situation. So if we have an ionic bond, we have an ionic compound, okay, as long as it's a true ionic bond. If we have only nonpolar bonds, we have a nonpolar molecule. If we have only one bond that's polar, then we'll have a polar molecule, okay? In the 4th situation, this is where we have more than one polar bond. Okay. In this situation, there are 2 options. So if we have more than one polar bond and we're symmetrical, then we create a nonpolar molecule. But if we have more than one polar bond and we are non-symmetrical, then we have a polar molecule. And so this situation is the only time where the symmetry of the molecule makes a huge difference. Okay, so we have more than one polar bond, but we are symmetrical. That creates a non-polar molecule. If we have more than one polar bond, but we are non-symmetrical, then that creates a polar molecule. Okay, so we're going to do a couple more examples just to have a look around these rules, and then there's going to be a little bit of practice for you to do as well. So the next example that we're going to do is going to be N2, so some nitrogen. Okay, nitrogen, when we draw the Lewis structure, has a triple bond. Okay, and the difference in electronegativity between nitrogen and nitrogen is 0, which means we have a non-polar bond. since we have a nonpolar bond, and it's the only bond we have, this is a linear molecule again, but since we have a nonpolar bond, only no polar bonds, we are going to have a nonpolar molecule. Okay, in this instance, that's because we only have nonpolar bonds, so that creates a nonpolar molecule for us. Okay, now the next example that we're going to do is we're going to have a phosphorus, and it has 4 bromines and a chlorine on it. So when we draw the Lewis diagram for this, phosphorus is going to be in the middle. There are 4 bromines and a chlorine that are around this phosphorus. And each of them has their 6 outer electrons. Okay. And when we do the difference in electronegativity, we have to do 2 because we have to do the difference for our phosphorus bromine bonds as well as for our phosphorus chlorine bond. So the phosphorus to bromine, phosphorus is 2.1, bromine is 2.8. So phosphorus to bromine is 0.7. And phosphorus to chlorine, phosphorus is 2.1, chlorine is 3. So it's 0.9. Okay, so both of those are polar bonds. So we definitely still have our polar bonds. Okay, when we look at the shape for this molecule, the shape for this molecule is going to be, let's see, we've got 5 things around the middle here. So we're dealing with a trigonal bipyramid. Now here is where this one actually gets tricky. So a trigonal bipyramid is normally symmetrical, but in this case, it is non-symmetrical. And that's because the bonds in this trigonal bipyramid are not all the same. Since we have different types of bonds, it is no longer a symmetrical shape. So we have polar bonds, but we have a non-symmetrical shape. So we are going to be dealing with a polar molecule. And so we're going to have that situation where we have polar bonds, but we have more than one. So we have to look at the symmetry. This is a non-symmetrical shape because the trigonal bipyramid bonds are not all identical. Okay, and that's the big trick here, is that trigonal bipyramid is normally symmetrical, but since the bonds are not all equal, it is now no longer symmetrical. And in order for our polar bonds to turn into a nonpolar molecule, they would have to be symmetrical. Okay, and so that's the lesson on molecule polarity. There's a ton of practice. Please make sure that you do the practice. Okay, and I will post an answer key to go with that practice as well so that you have lots of practice with this molecule polarity.